So we have shown that uij equals a plus b, and this b, the second term, is just bij. This is because in this sum, the only contribution comes from the case when k equals j. And therefore, this is just bij. Now we have to compute a. And again, note that if k is t, then the event x1 equals k would imply tau is at least 2. Why? Because we are starting, remember, from I, which is already in t. So both I and k, which is x0 and x1 respectively in this case, are in t. So therefore, the first time the Markov chain will exit, t has to be at least 2. It hasn't exited in the 0th step and the first step. So therefore, the first time it will exit is at least 2. So we'll use that in this calculation. So remember, A is this sum. A is the sum which corresponds to the case when the first step is still inside T, which implies tau is bigger than or equal to 2. So therefore, I can put tau is bigger than or equal to 2 inside this sum. This already implies this event, so I can of course put it in. So this is not going to change the event. So for each k, this is the case. For each k in this sum, I can put tau bigger than or equal to 2, and then this is actually a bigger event. So this implies this. So this is a bigger event. So if you intersect with a bigger event, nothing changes. Now, of course, tau bigger than or equal to 2 can be split into tau equals n, where n runs over 2 to infinity. So for each k, I have this sum inside. Now, of course, tau is equal to n, so this x tau would become xn. So because of tau equals n, I can replace the x tau by xn. Now, tau equals n means the first time the Markov chain exits t is in the nth step. That means before the nth step, the Markov chain has not exceeded t. So that means, of course, first step it hasn't, because it's coming from a transient step, but we will still write it. So starting from I, we will first be at x1 equals k. So first step will be at k. Then x2 all the way up to xn minus 1. All of this will be inside t. We are still inside t. And xn will be outside t, but xn will be actually j, which is taken to be outside t. So therefore, automatically this will imply that tau is equal to n. So essentially, tau equal to n in this event will force that x2, x3 all the way up to xn minus 1 are all inside t. So you haven't exceeded t up to time n minus 1. The exit happens exactly at time n where it reaches g. So this is what we have shown. Now we'll use the Markov property in the form of MC, the definition of Markov chain. So note that this can happen. For each term, this guy would be equal to. First, you go from I to k in one step, that is pik, and then you restart your clock. Start at k, and then you restart your clock. So instead of x2, in the new clock, this is x1, because you are starting again at k. And then the x3 would become x2. All the way up to xn minus 1 will become xn minus 2. And then xn will become xn minus 1. So using MC, we can show that this is equal to this. Each of these probability here is equal to this probability, and therefore the sum is equal to this sum. So we have done such calculations before many times, so we should be used to by now. Now note that this just means that's PIK, for you can forget about that. Just consider this probability here. This means that starting from K, and remember K is in T, so K is already a transient state. First, n minus too many steps are still in T, they're in transient states. And the n minus 1th step is J. So this means this part just means that first time this Markov chain exits T is at the time n minus 1. Because at the time 0 it hasn't, because 0 K is in T. X1 is still in T, X0 is in T, X1 is T, X2 is in T, all the way up to X minus 2 is in T. Xn minus 1 in equals J, which is not in T. We have taken J to be not in T, right? So therefore, first time it exits T is n minus 1 and X minus 1 equals J. So these two events together is just this event. This is something we have done just before. So we are just using a similar argument here. Now note that this means n is running from 2 to infinity, but n minus 1 is going to run from 1 to infinity. So this is just saying tau. Okay, so maybe before that we should make one more change. Here, tau is n minus 1 and x minus 1 equals j. So therefore, this is just tau is n minus 1 and x tau equals j. So and instead of n minus 1, I can put tau, since on the event tau equal to n minus 1, that is the case. Now this sum here, this n bigger than or equal to 2 would give you that tau is bigger than or equal to 1. So this sum I can take inside, and of course PIK has no n in it, so this can come out, and this sum here will give you tau is bigger than or equal to 1. Now of course, since we are starting at K, which is in T, first time the Markov chain hits T complement has to be at least 1. So tau bigger than or equal to 1 is redundant, since we are starting the Markov chain at a transient state. So we can get rid of that. So that will give us this sum here. Sum over K in T, PIK times PK of tau x tau equals J. Now recall this is just UKJ. So this is summation PIK UKJ. So that shows that the first term A is exactly what we needed it to be. So if you combine these two, we will get that. We have already computed B, which was Pij, and A was this term here. So therefore, what we have proved is that for each I in T and for each J in T complement, Uij is just equal to this sum, which is star star. So this proves star star. Now, the interpretation of star star is as follows. So exiting the state T, exiting the set T of all transient states, okay, by hitting the state J can take place in two ways. Okay, Uij is the probability that starting from I, we exit the set T by hitting the recurrent state J. Right? So that can happen in two ways. Either it is accomplished in one step. So you go from I to J directly. That happens with probability Pij. That gives the second term here. Or if not in one step, then you have to first make a transition to an intermediate transient state K in the first step. Okay? That was part of our first step analysis. This happens with probability Qik or Pik, whatever you want to write. Pik and Qik are same if K is in T. And then from K, the chain must exit T by hitting the state J. That has probability UKJ. So therefore, that gives you this sum by Markov property, of course. So therefore, exiting the state T by hitting the state J can happen in two ways. Either you do it in the first step itself, which happens with probability Pij, or you don't do it in one step, in which case the first step would be a transient state. You first go to another transient state. That happens with probability Pik. And then from that transient state K, you go to J eventually. Okay, so what I mean is from that transient state K, starting from that transient state K, you exit T because hitting the recurrent state J. So that happens with probability UKJ. And then the product comes because of Markov property. And then you have to take the sum because this K is arbitrary. This has to be one of the transient states. So that is the intuition or the heuristics behind star star. This is the interpretation of star star. And what we have actually done in the proof is we have just formalized this heuristic. Most of the cases we first give the heuristic and then give the proof. In this case, I actually gave the proof first and then gave the heuristic so that it becomes completely clear what is going on. So this is what we mean by first step analysis. Whether exiting happens in first step, which is this probability, or it happens in more than one step, which is this probability. Okay, so this completes our discussion on absorption probabilities. And as we have discussed, we have already computed the probability of A being ruined with the help of the theorem on absorption probabilities. And then I gave you one more exercise when solve the gambler's ruin problem in the other case, namely when the coin is unfair, the coin is biased. And there are more examples in the book that I would like you to go through yourself.